Greetings and welcome. My name is Katie Kimberling. I'm a member of Team 5 in the USD MADS Course 509, LLMs for Data Science. We introduce to you our exciting project, A Seismic Shift for Generative AI, whereby our team integrated AI into United States Geological Survey data for extended earthquake analysis. Seismic activity is increasing, producing an increased volume of data. Population densities in urban areas are on the rise, and earthquakes are also increasing in more rural areas, such as Oklahoma and Texas, due to fracking in the oil and gas industry. In an emergency situation such as an earthquake, first responders face time constraints, unknown circumstances, limited resources, and very high stress. While trained for such situations, no two are the same, and the fast pace and unknown, unique state of affairs for a particular seismic event, combined with human lives on the line, increase the chance for error. Furthermore, the incident commander or emergency manager, as the head of a first response team, must make quick-paced decisions with available information and resources while trying to predict what might imminently occur. While the USGS provides data updated on a minutely basis, it is not always user-friendly, especially for non-technical audiences. We employ generative AI as an additional tool in the data pipeline to aid the team leader and the general public in a broader, more user-friendly understanding of the event at hand, including easy-to-understand visualizations and RAG-generated, data-based suggested protocols, with the hopes this will result in more lives saved, fewer casualties, and reintegration of infrastructure as quickly as possible. My teammates are going to walk you through the details of our pipeline, but a broad overview of the workflow resembles a bit of a chutes and ladders game. First, the USGS API scrapes data from the past 30 days. EDA cleans this data to retain only US seismic events with magnitudes greater than 2.5. Via feature engineering, these magnitudes are categorized and summary statistics are calculated. GPT 5.2 is then integrated to provide key findings, recommendations, and some summary charts. A Streamlit dashboard employing a RAG allows users to generate reports for selected events or obtain protocols for seismic events similar to what they might experience in their area.
For my part of the project, I handle the data injection and exploratory data analysis. Earthquake data were collected from the USGS API, pulling the last 30 days of activity with a minimum magnitude of 2.5, filler to US territory only. A geographic bounding box was applied, covering latitude 18 to 72 degrees north and longitude negative 180 to negative 65 west. This captured all 50 states, Alaska, Hawaii, Puerto Rico, and the U.S. Virgin Islands. Since the bouncing box also picked up neighboring countries, a post-fetch filter removed 44 non-U.S. records, including 18 from the Dominican Republic, 17 from Mexico, and 4 from Canada. The final result were 766 U.S. only earthquakes from initial 810, covering January 15 through February 14, 2026. Once the data were fetched, the next geoJSON structure were converted into flat panda data frame with 766 rows and 12 columns, including event ID, magnitude, play, time, latitude, longitude, and depth. Timestamps were converted from millisecond to proper data time format. Basic statistics were then calculated. Magnitude averaged 2.98 with a standard deviation of 0.49, ranging from 2.5 to 6.0. Depth averaged 29.9 km, ranging from negative 3.4 to 218.2 kilometers. The mean latitude of 47.8 degrees north confirmed the data is concentrated in Alaska. For data quality, we found zero missing value across all 12 columns, zero duplicates, and zero invalid coordinates. However, a negative depth value were flagged for cleaning. Finally, two features were engineered: magnitude territory and reason label extracted from play string. A five-step data cleaning pipeline was applied. Step 1 through 4 check for missing magnitude, duplicate, invalid coordinate, and invalid magnitude range. All removed zero record, meaning the USGS data were already very clean. Step 5 remove 8 records with negative depth values, reading the dataset from 766 to 755 records, a 99% retention rate. For the ski statistic, over 29 days, there were 758 earthquakes, averaging about 25.5 per day. Mean magnitude were 2.98, ranging from 2.5 to 6.0. The vast majority, 95%, were minor magnitude, with just one strong event, a 6.0 of the coast of Oregon. By region, Alaska dominates at 60%, followed by California at 17%, Texas at 4%, and Puerto Rico at 4%.
So now we move from exploratory analysis into automation. Instead of working with a static dataset, we built a live ingestion layer that pulls the earthquake data from the USGS API. The fetch earthquake data function retrieves the last 30 days of earthquakes at a magnitude of 2.5 or higher. What's important to note here is that we enforce the US-only geographic filtering before any downstream processing. We do this by restricting the latitude and longitude to the defined US boundaries, and we ensure that every record that is entering the pipeline is geographically valid. This early filtering improves the reproducibility, scalability, and also ensures that our AI summaries are based on the data that's actually relevant to what we want to see. So once we've ingested the earthquake data, the next challenge is how it's structured. It comes in the form of a hierarchical GeoJSON, which is not immediately ready for us to analyze. So we then use the parse GeoJSON to data frame function to flatten each earthquake feature into structured columns, including magnitude, depth, latitude, and longitude, and tsunami indicators. We also converted timestamps from milliseconds into readable date time. Once structured, we run the descriptive statistics to validate the magnitude ranges, depth distributions, and coordinate integrity. This validation step ensures we detect anomalies or unrealistic values before integrating modeling or AI interpretation. In short, this slide represents our quality control layer where we're making sure what we're feeding into the AI actually makes sense. So now we know the data is valid that we're looking at, and it's also structured correctly. Once we're there, we can integrate generative AI through OpenAPI's API. It's important to emphasize here that the AI model is not performing numeric computation. All statistics, counts, and trends are calculated in pandas first, and then we pass those structured outputs, such as summary statistics and notable events, into a carefully designed prompt. The model translates those quantitative findings into stakeholder-ready explanations, including executive summaries, key findings, and recommendations. Because this layer is modular, we maintain separation of responsibilities. So data ingestion, cleaning, and validation happen independently from the AI interpretation. This architecture reduces hallucination risk and improves transparency, since the AI is interpreting verified outputs rather than generating raw analysis. This is particularly important when dealing with something like trying to come up with protocols and suggestions for earthquake events. We want our data to be reliable, and we want the process to be transparent for our stakeholders.
Hi everyone, my name is Paola, and my part of the project was building the Streamlit app that basically it turns our analysis into something interactive and usable. So on this first slide, I wanted to talk about the development of the Streamlit app. The app has two main tabs. The first is the briefing dashboard, which generates an executive style earthquake activity briefing, and it also displays our charts. The second is a protocol generator using RAG, retrieval augmented generation, and that is where the model is forced to use only evidence from the local knowledge base files. The app also saves key outputs like briefing.json, protocol.json, and the stat pack, so we can track exactly what the model saw and produced. On this slide, I included a screenshot of basically the overview. On the left, you can see the different JSONs, and then in the middle, you can see the two tabs, the briefing dashboard and the protocol generator. All right, so let's discuss the briefing dashboard tab. So essentially what it does is that it loads the cleaned earthquake dataset and a pre-computed stat pack that summarizes the time window, counts, magnitudes, depths, and regional patterns. So when the user clicks generate, we send the model the stat pack plus a curated list of top events and ask it to return strict JSON with specific keys like executive summary, key stats, notable events, and recommendations. The charts are generated from our data, and the app supports exporting a single file HTML report that can also be printed to PDF. And on this slide, I did include two small screenshots of what you see on the briefing dashboard tab. So on the left top, you have your briefing in figures, and there's the button that you can click on to generate an AI briefing. And then the bottom screenshot is basically the notable events, recommendations, and limitations. On this slide, I'm showing the Gen AI controls we added to make the app flexible and transparent. The main idea is these settings change what context the model receives and how consistent or varied the output will be. So first, top events to send to the LLM, or top_n, controls how many earthquake events we include in the prompt when we generate the briefing. So if we raise that number, the model has more candidate events to choose from for the notable events section, and it can produce a richer summary. But it also increases the amount of text we send, which means essentially more tokens and usually a slower or more expensive call. Next is the OpenAI model field. That's simply which model is doing the work behind the scenes, both for the briefing and for the protocol generation. So different models can behave a little differently in terms of tone, speed, and how strictly they follow formatting rules. Then there's reasoning effort for the GPT-5 family. And you can think of this as how much deliberate thinking we want the model to do. Higher effort can improve structure and reduce sloppy mistakes, especially when we're asking for strict JSON output, but it can also increase latency and cost. And finally, temperature controls. They basically control creativity and variation. So lower temperature gives more consistent, repeatable answers, which is usually what we want for an executive briefing. Higher temperature can make the wording more diverse, but it can also increase variability. So we keep it relatively low for stability. One important detail we built in is a compatibility check. Some model and reasoning configurations don't allow temperature. So instead of letting the app crash, we detect that case and automatically disable temperature in the user interface. That way, whatever settings the user chooses, the app stays stable and the user can clearly see which parameters are being applied. And we did this because I ran into that exact same situation where I was testing a different model and it wasn't allowing for temperature. And the entire application would crash. So we added this as basically um, a safety net. Um, and on the right here, I did include a screenshot of the Gen AI controls just for your reference. On this slide, we review the RAG protocol generator. The point of this is to create a protocol that is grounded in evidence and not just general knowledge. So the app loads text documents from the KD folder and then splits them into smaller chunks, so retrieval works better. That's why you'll see something like loaded for KB files, 17 chunks. Then for a user request, we retrieve the top K most relevant chunks and only send those passages to the model. The prompt enforces strict rules. Use only the evidence and cite it using IDs like E1 and E2. And if the evidence doesn't cover something, the model is supposed to put it into limitations instead of guessing. And I did include a link to our Streamlit app. You can just click on literally on the link that says Streamlit app, and it will take you to there. It will deploy the app for you. On the next couple of slides, we have Katie, who will be doing a deeper dive into the RAG protocol generator and some of the KB files that we used.
For Retrieval Augmented Generation, or RAG, integration into our Streamlit app, we manually created a knowledge base consisting of multiple database text files, which were summarized and paraphrased into structured documents from the FEMA and Ready.gov websites pertaining specifically to activities surrounding earthquakes. We did not conduct web scraping. The scope of this project was not to include dynamic updates, and we were not building a production emergency platform, but rather wanted to give high-level general protocols to those inquiring about various aspects of earthquake preparedness or how earthquakes might impact urban versus rural settings. To use the RAG, go to the Protocol Generator tab of the Streamlit app and use the drop-down menu at the top to select an earthquake event. This is depicted in the top graphic with the red arrow indicating the drop-down menu. In step 2, the middle graphic, the user selects how many knowledge-based chunks to retrieve. A lower K offers a tighter, more focused protocol, whereas a larger K value is broader but may introduce noise. Generally, 3 to 5 documents to pull from are recommended. The RAG then goes to the knowledge base folder and searches for key terms within the provided documents that are similar to the magnitude and general regional area of the earthquake event the user selected, then feeds those passages to GPT 5.2, which then generates a user-friendly, easily understandable, non-alarmist, and ethically sound protocol. A snippet of an example of this is provided in the bottom visual. This markdown can then be downloaded as a JSON file, and the exact prompt and the exact chunks of text retrieved from the provided knowledge base documents can be viewed for transparency as an ethical consideration.
In conclusion, this project has shown us that generative AI is a very powerful tool, and it is even more powerful when it is layered on top of structured, validated workflows. We didn't use AI to replace analysis. We used it to interpret verified outputs and make them accessible to non-technical stakeholders in an accelerated fashion. Through building the ingestion pipeline, the validation checks, AI briefing system, and RAG protocol generator, we saw how modular design increases transparency and reduces hallucination risk. Looking forward, integrating additional real-time data feeds and building feedback loops could make the system even more adaptive and responsive. Ultimately, this project reframed AI not as a replacement for data science, but as a structured assistant embedded within a carefully designed analytical architecture. It was a pleasure working with this team and learning so much on this project. Thank you.